Welcome everyone. Today it's our pleasure to have Apurva Nakade from the University of Western Ontario, who will speak on an application of Gromov's H principle to manifold calculus.
All right. Yeah, thanks a lot for this invitation. I've never been to Regina before. It's a very nice university. It's like it protects you from the outside. No, but really, it's a really nice university. I've been roaming around the whole building. It's very pretty. Yeah, so I am going to be speaking about two things: H principle in manifold calculus. What is H principle? It is a homotopy technique. I would say for studying geometrical problems, and I'll explain this term more precisely. And what is manifold calculus? There are experts about this in the audience, so I'll only be brief. You can ask them later. It is a homotopy theoretic technique for studying embedding spaces. And so basically what I do is, in my work, is I try to combine these two different areas to answer a question that I was interested in from symplectic geometry. I'm not sure if I'll reach the symplectic part, but I'll at least give a sketch of this. Please feel free to interrupt me if you have questions in the middle or anytime if I'm not clear. All right, so I'm going to start with what is Gromov's H principle. And my goal is still in progress, is to study Lagrangian embeddings in symplectic manifolds. And you can see here's the name of embeddings are exactly what manifold calculus studies. So I was interested in seeing if I can use manifold calculus to study a special kind of embedding, which is Lagrangian embeddings. Okay, and there's partial success, and there is a lot of more work to do here. Let me start with what Gromov's H principle is about. The H here stands for homotopy. And what is Gromov's H principle? The first example of H principle was discovered by Smale, and it was for immersions. So let M and N be smooth manifolds. And let what is an immersion? Just quick recall, immersion is a map I from M to N such that Di is injected. So Smale wanted to study immersions between manifolds, and he realized that this space is actually homotopy equivalent to a space which is much simpler. And this is monomorphism from Tn to Tn, which is vector bundle again, and I'll state the theorem and then I'll pause. This is by Smale. Smale proved it for spheres and Hirsch generalized it for higher dimensions. If dimension n is bigger than m, then map
So what's the vector bundle monomorphism?
Sorry?
Yes, it's supposed to be something over the base?
Yeah. So it is just a map that lives. You have these vector bundles that live over M and N. It's just a map of vector bundles which is fiber-wise injected.
And the map from M to N is just like any continuous map?
Any continuous map. Yeah, exactly. So that's the key. That over here we have no restriction on what the base map is. Whereas here the base map is injective. And what Smay's theorem is saying is that if the dimension, this is a very weak restriction, you just want this to be one dimension lower, then you can just get rid of the base restriction and only consider the fiber-wise data. And this is the first example of edge principle. And that's what all edge principles do. They somehow say that you can somehow like separate the data of the bundle from the base. So here I want this map to be injective and this to be any continuous map. And there is no relation between this and this except that it lies over the base. It is not the differential of this.
And you said we insist on the emergence being injective, or we allow some self-intersection?
We allow self-intersection.
Oh, that is allowed.
Yeah, that is allowed.
Okay.
Oh, so this should have been is fiber-wise injective.
Yeah, sure.
Thank you. So for example, emergence, standard example of an immersion is this is an immersion of S1 in R2, but it's not an embedding, it's not an injective. This belongs to immersion of S1 in R2. And in fact, Smale used this to prove his famous sphere eversion, where he studied the space of immersion from S2 into R3 and showed that it's connected by using that homotopy equivalence. And that it says that the natural embedding of S2 in R3 is homotopy equivalent to the antipodal embedding. Maybe, okay, here's an aside. It's if you are seeing this for the first time, this is worth knowing. Smale used this to prove that the natural embedding of S2 in R3 is connected via emergence to the antipodal embedding. And this result is called the sphere eversion. there are very nice YouTube videos about this. They show how to do it. But when Smale did it, we didn't know how to, a constructive way. He just showed that it's path connected, and so there has to be a path connecting those two embeddings. And so this is the sense in which H principles connect reduce geometrical problems to homotopy theory, because you can study the homotopy type of this space much easier, much easier than the homotopy type of immersions. Immersions.
Yeah, how many people can get that this is the equivalence of the map? The map.
Are you
That's the idea, yeah.
What is Smale's idea of proving that? Let me see if I can say this quickly.
Or just what, yeah, techniques.
What you show is that if I give you a data like this, if I give you a bundle morphism like this, you can perturb it to get an immersion. So the way H principles are proven is you show that so the idea is given group is given a bundle morphism f from Tm to Tn lying over some map declared from M to N. We can perturb f or little f, comma, perturb and this is you do some analysis. This is a constructive proof. You do it locally and you show it can be patched up. You show that locally, if M is just a small neighborhood of a point, and if I give you a small neighborhood of a point, so what does that mean? I can send the whole thing. So let's say this is M, and I send the entire small segment to a point. But then I also give you like a monomorphism that sends each tangent plane here to some, let's say this is hard to say, so I'll just say do this locally. Do this locally by hand. So on a small neighborhood of a point, given a monomorphism, because the tangent data is exactly like the base data, you can shrink as small as you want, and then use the tangential morphism to perturb the base, and then patch it up. Patch together all the local perturbations. And that's how you do it. Given one monomorphism, you constructively do it. And then what you do is, the next step is we do these perturbations. Parametrically. What this means is if I give you not one monomorphism, but a family of where S is in any topological space S. So if I have a varying family of bundle monomorphisms, I can use this exact same technique, little souped up, to do it parametrically. And now if I can do this for all spheres, then there's a formal mechanism that says that it's a weak homotopy equivalence. So you can say that phi naught is isomorphism, then pi1 is an isomorphism by doing it over S1, then pi2 is an isomorphism by doing it parametrically over S2. And this is analysis, and then this is just some formula. Is that good? Yeah. I can tell you more later. So for his technique has a name, it's called convex integration. It's a very constructive thing. You do some integration by hand and construct the immersion. Okay, so this H principle is for immersions. Any other questions? Now I want to state the H principle that I'm interested in, which is for embeddings. And this was by Gromov. Now this is Gromov's directed embeddings. So if you look at what you have here, we are saying that if I give you a bundle monomorphism, I can perturb it to get an immersion. Now it's too much to expect that you can perturb a random thing to get an embedding. Because embedding is saying, for example, a bundle monomorphism can send the entire manifold M to a point and be injective on the tangent spaces. So you're saying you start, if I crush the entire manifold to a point, then can I perturb it to get an embedding instead of an immersion? And it's not clear it can be done. So Gromov's idea was that this exact technique is not going to work immediately, but maybe you can change it slightly, and you'll get an H principle for directed embedding. So this is going to need some setup. So that's what I'm going to do next. So instead of immersions, now I'm going to talk about embeddings. And this needs a little notation. As before, we have manifolds, and now I need to define a new space. What this means is that this is a fiber bundle over N, and the fiber over point Q is the set of M-dimensional subspaces of T, Q, so it's the M-plane Grassmannian bundle over N. Right? And let A be a subset. This is just setting up the H principle statement for embeddings. It needs a little more notation. Now note that version I from M to N defines a map. I'll call this GR comma I. Basically, if I have an immersion like this, then this is my I. then I send this point to the image of P, and it's sending P to the image of TP.
So here you set up that M is less than N.
Yes. So emergence naturally defined maps to the Grassmann bundle, and here's where directed comes in, and immersion is A-directed, and immersion I is A-directed if the image of GR I. So all the tangent planes map to this specific subset of your Grassmann. And so for example, a very weird thing I can ask is I want none of my tangent spaces to be vertical. So A would be the complement of the vertical direction. And then I'm looking at immersions where no tangent is vertical. So in this case, that won't be an example because here this point is vertical. So by choosing different A's, I can put restrictions on what kind of immersions I'm looking at. And in fact, turns out these are the embeddings that we're interested in. These are the immersions that we're interested in geometry. And injective immersion. Is called an embedding. This is not exactly true. There is some more thing you have to say, but I'll kind of leave it for now. There's some extra thing you put in here about the image. Okay. And actually, I only need. So here, an immersion is an embedding if it's actually injective on the set level. It's not just fiber-wise injective. Is the space of any questions? And Gromov mimicked mimicked or generalized Smale's methods to give a slightly easier description of this space under certain circumstances. So that's the H principle for directed embeddings. And what is the slightly easier description? It goes like this. I'll say define this, or let me put it this way, formal immersion or I'll just go to embeddings. It's a map. E is an embedding. E from N to N. formal iterative embedding is an embedding E where there is no restriction on the E. So this is like D. This is like separating the tangential data from the base data. So I'm not saying DE is inside A, but what I'm giving you an extra data, which is a tangential homotopy that connects DE to A. And I'll describe what tangential homotopy means. A tangential homotopy. Yeah.
So here in this example, you see that A in this example, A is what?
Okay,
this
so let's
example,
let's do an example. So for example, I can say let's take M to be S1, N to be R2, and GR1, TR2 is all the lines in TR2. So at each point you have all the lines there. And then I can say let A be the lines which are, I'll say, not vertical. Oh, actually, to give an example, I'll use M equals to R1, just because in this case there exists such a thing. Then embedding A, R1, R2 are maps, are injective maps, smooth injective maps from R1 to R2, such that at no point which are not vertical anywhere. So an example would be something like you map this to something like that, and this is inside my embedding space. But if I have something like this, where now I have a tangential this, then this is not in my embedding space. So like what I'm doing using A is I'm restricting what the tangential data can be on my manifold. Is that?
And in that setup, A is allowed to be empty if I want all embeddings?
You would want A to be GR if you want all embeddings.
Oh, sorry, that's where you want. Okay, it's not the excluded one; it's the allowed ones. Yeah. Okay,
exactly.
So if it's everything, then you get all embeddings.
Yeah, exactly.
Yeah, okay.
Yeah, so you can exactly.
Good.
So for example, and yeah, so this is one way to enforce tangential structure by using the Gauss manifold. And what formal embedding is, it's saying I'm not forcing my differential to be not vertical. I just give you extra data which takes my derivative to something that is not vertical. So here's an example. Let me take a formal embedding, continuing this example. Would be something like this. I take this embedding. I don't care about the exact tangential data. I use the same A. But what I do is at each point, I give you a map that goes from its tangent line to something that is not vertical. So I can keep it constant. I can slowly move it vertical, horizontal, for example. I can do something like this. I can make this perturbation smaller and smaller. So is that picture fine. So I don't in a formal embedding, I don't say that the tangent space is horizontal or the tangent space is non-vertical. All I say is I have a perturbation of each tangent space, which is non-vertical, and I keep that data with me. So a formal embedding is so is this map E, but along with E is the pair E and gamma, where gamma is a path of tangent spaces or path of subspaces is a path in GR and GN. So at each point, I give you perturbation that takes this tangent line to something that is non-vertical, and I keep that data with me. So it's a pair E comma gamma. But notice that there is no restriction on what DE should be. And you can imagine that this is a bigger space than this. I just need E to be an embedding, and I need some tangential data with it. And here's the same generalization by Gromov. And the proof is, again, similar. It's perturbative. You do it locally and you patch things up together. It's called using convex integration. And he proved that if, so this one I'm not going to state precisely because it's very technical. If A is a something he calls convex ample open subset, but I'll just say it's a large open subset. Then embedding formal embeddings is a weak homotopy equivalent. And what is the map that goes from embeddings to formal embeddings? I just take the constant tangential homotopy because my tangential data is already in A. And I need something that connects from DE to A, so I just take the constant tangential. And the way you think about this is, what this is saying is if I give an embedding which is not the right embedding, but I also give you some tangential data that goes from that embedding to the thing I want, then I can use that to start slowly perturbing my manifold and make it non-vertical, or make it lie in D. For example, I don't know if it's possible for this example because I might have created an impossible one. But let's say, so the usual picture that are drawn there are something like, so the general picture is something like, if I have my manifold M, or this is E of M, and I have, starting from my tangent thing, I have a perturb like that. From here, I'm giving you some perturbations, and I'm giving you a tangent homotopy that goes from this perturbation to this perturbation. Then what ends up happening is you get things which look like so. I don't know if you can see the green, but the white one was my original tangential, original embedding, which had these pink tangent bundles, and I wanted the yellow ones. And I do some small perturbations in each patch, and it ends up giving me something in my required tangential direction. So the white one is my initial embedding. And the green one is my perturbed embedding. go from initial to the perturbed one using this tangential homotopy that goes from the pink thing, which is dE, to my yellow thing, which lies inside A. So somehow at each, I do this locally, I use this data to perturb it, and then I do it here, and then I do it here, and then you do some calculus to patch it.
And in Gromov's theorem, is there a condition on the codimension, or just is at least one and that's fine?
So it's forced by this largeness condition.
Oh,
Yeah, it's very technical,
okay.
but
But it ends up putting a condition on the codimension.
Yeah.
Okay.
Yeah.
Thanks.
Yep.
Well, if A is the whole thing, is the harmonic. Is that large?
Yeah, but then this is tautologically true, because then you are saying A directed.
Yeah, that's the space of embeddings, yeah.
Yeah.
And the other thing.
Exactly.
But yeah, the other thing is this a formal.
So formal, I personally raised here. Formal is
Yeah, you have that extra information.
extra information. But if you're just looking at all embeddings, formal embeddings also have an embedding in them. So this is, in that case, it would say this extra information is redundant, like it's contractible. Yeah, so that's an overkill in that case. But for example, if you want to, like say, this example is not large, like it won't work here. Non-vertical in R2 won't work, but I'll just give you an example of largeness. Largeness, it's unfortunately very technical. Non-vertical in R2, non-vertical lines in R2 is not large. But if I have a non-vertical non-example, sorry, I'll use it right. So non-example and example. My non-vertical lines in R3 is large. It's something to do with if I look at the complement of a line in R3, the space is connected. It's codimension 2. But if I look at the complement of a vertical line in R2, it disconnects the space. So somehow you can't do some analysis to go from one to the other. But in this case, it's large enough. The codimension is small, and you can move around and perturb things.
Is this related to symplectic structures on open and closed manifolds?
Yeah. In fact, so this is a part of a mega opus by Gromov called partial differential relations. And this is one chapter, and another chapter is about existence of symplectic forms on open manifolds. It's the same technique, similar technique that lets you show that every open manifold of even dimension has a symplectic form, as long as there is no topological obstruction. Yeah. And it's the same perturbative technique. You start with something that is not symplectic, but then by patching local things, you can create something that is symplectic. Okay? So this is somehow you should think the right-hand side is flexible, and the left-hand side is rigid, and this is geometry and that's topology, and this is saying you can do geometry using topology as long as A is like a large thing. Alright, now I have 20 minutes, or 10 minutes, so I'll connect it to manifold calculus and I'll try to do as...
You can take 20.
Okay,
Yep.
Thanks. Manifold calculus is designed to study embedding spaces. So this was designed to study embedding spaces. And it's a natural generalization to ask, can you study directed embedding spaces? And the answer is yes, exactly when Gromov's principle applies. So you can study directed embedding spaces using manifold calculus exactly when A is large. So then we study A directed embeddings. Using manifold calculus. And answer yes, precisely when H principle, when Gromov's H principle applies. And it has to do with the fact that the space of formal embeddings can be studied using manifold calculus, but this space is our embedding space exactly when you have H principle. So now let me say what manifold calculus is. Yeah, I'll leave this there. Again, as before, M is a manifold. Let OM be the poset or the category of sets of M, where the morphisms are just inclusions. So you have the open set on which you define your standard sheets. And note or I'll just write it like this: E and B defines a functor which assigns to an open set U embeddings of U into N, and if you have a subset of U, then there is also the restriction is an embedding. This is a homotopy functor. A homotopy functor. F from O to top takes isotopy equivalences, homotopy equivalences. This is just a very natural thing to expect. So I wouldn't, if you don't know what isotopy equivalence is, it's not that complicated thing. And in this case, manifold calculus studies such functors. Manifold calculus studies such F. So it studies functors that go from OM to top, that take homotopy, isotopy equivalences to homotopy equivalences. So it basically studies free shields on that category.
The technical condition that you require the photo to be good.
Yeah,
yeah.
Plus one more.
Yeah, plus one thing.
Yeah, thanks.
Technical, yeah. Which is useful in the theory.
Yes.
Yeah, to characterize polynomial photos.
There's something about filtrations.
Filtration, yeah.
So there's one more condition here. And how does it study this? So inside OPM, you have this subcategory. Of open sets, diffeomorphic, many copies of Rm, which are basically disks. Finally, many copies of, maybe I should call it m-dimensional disks. So we only look at the subsets of M, which are like open disks. And you define this as the homotopy limit this is the definition. This is called analytic. So you have this subcategory of disks, and you reconstruct your functor using only disks. So you forget about what F does to arbitrary open sets, but you only look at what it does to disks. And then you create this huge homotopy limit out of it. And this is like the amazing theorem, which is central to manifold calculus. This is, you would really Weiss line. There's a series of papers that finally prove this, that if dimension of n minus dimension of m is bigger than 2, then T infinity is homotopy equivalent to 2. It's a very, very powerful theorem. It says that you can study embeddings by just looking at what embeddings are on disks and how they glue together. The very important thing here is this. And I should say why this is useful.
Actually, the condition is stronger, yeah. Like the dimension of M is there, and it's built by the homotopy dimension.
Right.
Of M.
So
It's kind of stronger, yeah.
Mark, we can replace dimension of M with the handle dimension of M. This is something to do with, if M is an open manifold, then it might not have the top cells or something, and you can drop the, it might not have top index things. It's something to do with handles, how we create handle order decomposition of M. That's the first remark. And second remark is disk M has a filtration given by disk less than equal to M. Where these are at the most k disks. So you look at subsets of M which are at the most k many disks, and you have this filtration of this big subcategory which induces a tower. And you do the same thing, you repeat this construction. The same construction gives us a tower, T1 f of M, T2 f of M, T3 f of M, and so on. It gives rise to a tower. To something called, this is called the Taylor tower. Something like that. And we know we can classify fibers. I just say homotopy fibers, but that's technically not needed. So we can classify the homotopy fibers of this tower. So you have a tower. In this case, the limit of this tower is the original functor, and you also know the limit of the level at each thing. And you would hope that you can patch up this data. Or for example, there's a spectral sequence now that that can go from the fibers to the whole thing. Is it from the fibers or the spectral sequence that you construct?
Spectral sequence?
The spectral sequence for computing this?
It's spectral sequence for T infinity.
Yeah, for T infinity?
Only T infinity.
Yeah, but that
But for the tower, for TK, we don't know how to do that.
Okay, so there's a spectral sequence that can compute T infinity of things like that. So there's computational tools that we can do there. And there's one more thing, which is the T1 of embeddings, M comma N, turns out to be immersions. M comma N, if again, let's say, dimension N is bigger than dimension M. So what is happening is you're starting at immersions and then you're adding more and more data and creating embeddings. So that's actually the title of the paper where this shows up. It says embeddings from the point of view of immersions. And that's the philosophy. And I'll just state my theorem and stop there. And what I basically say is that Gurveli's theorem is in fact true. Gurveli-Weiss Klein theorem is also true for embeddings A and N if Gromov absence. Holds. Basically, we can use this machinery that has been created in manifold calculus to study not just embeddings, but also A-directed embeddings.
Formal, study A-directed embedding, true formal.
Well, sure, but because Gromov's theorem says it's a homotopy equivalent, So the formal embeddings have no geometric significance. They are simply to connect this theory with homotopy theory. It's like this space is by itself not very interesting.
That question could be phrased differently. I mean, do you get, is this theorem true always for formal embeddings, independent of whether they're large or not?
Yes. So this theorem is true for exactly. This theorem is true for formal embeddings independently. Yeah. And in fact, so I was interested in what happens when A is Lagrangian. Lagrangian is not large. What turns out you can, so what happens, I won't state this precisely because I'm already out of time, is that if you try to do this for Lagrangian embeddings inside a symplectic manifold, it turns out that Lagrangian, you can make this precise, is not large. And so when you apply T infinity, what ends up happening is you end up enlarging your embedding space. So what ends up happening is TR is a large subset of TR and TM. where TR stands for totally real. So when you apply manifold calculus to this space, it expands it and it throws in extra embeddings which are not that interesting. And so what I'm trying to work on next is, can we refine the tower? Can we replace? So the question that I'm currently working on is if current work that I'm mostly working on is if M has more structure, can we replace disk M by a finer category, and hopefully we'll get a tower that is richer and that can see more structure. Yeah, basically that's what I'm trying. For example, I'm currently trying to see if M is a G manifold. If a group acts on the manifold, can we look at equivariant disks inside your manifold and have a tower that is not linear but like has some kind of a subgroup structure in there. Basically, so if you want to apply manifold calculus to geometry, we need to create some new tower that will see more, and that's the goal. And that's my talk. Sorry for going.
Are there any questions? Actually, I had one.
Yeah.
It's interesting going from Lagrangian to totally real. Do you have a more general statement that says if you look at A-directed embeddings where A is not large, then T infinity gives you some embeddings with respect to some enlargement of your A, or is that a special case of a theorem of that form?
Yeah, exactly. Actually, I don't know if it's possible to always enlarge a subset. But if you have an enlarged one and they are homotopy equivalent, then this turns out to be a special case of that.
Oh, that's all you need. You just need the other one to be large and homotopy equivalent to the small one.
That's it.
Huh.
Because that's the essence of H principles. They reduce geometry to topology, and topology doesn't differentiate between homotopy equivalent things, and that's it works. Yeah. That's exactly what happens. And this is something like. I can even tell you why this happens. This is something like UN mod ON bundle, and this is something like GLN C mod GLN R. And this is like this deformation retracts onto this. But more generally, if I had any A, and which was a subset of A prime, and this was a homotopy equivalence, then you would get the same T infinity. Or T infinity of this ends up being that.
How about things like symplectic embeddings or pseudo-holomorphic curves?
Yeah, so
can you use this kind of thing for that?
So another thing that I'm trying to figure out is what is not known is configuration spaces of symplectic embeddings. Like if I give you a ball and I try to embed a smaller ball in there, or two smaller balls in there, we don't know what that configuration space looks like. Like even like that simple question is still not answered.
Because the size is important.
The size, yeah, exactly. That's why I said we need a finer category. Exactly. So if M was say symplectic,
oh, I see.
Then
So that would be an abstraction to doing this kind of thing for symplectic embeddings of one manifold. Right?
Exactly. Yes. In fact, I don't know this precisely, but I think there's something like this being done for Riemannian manifolds, where you try to embed you study isometric embeddings. But now the radius is important. So you have configuration spaces, but disks with sizes, and study how they're. So, I think it's so little is known about symplectic that I'm more inclined to work about equivariant manifolds and Riemannian manifolds first, see if there's something there, and then try to go back to symplectic. Like it's these days they call it a packing number. Like how well can you pack disks inside a bigger disk? And you have some things like it's connected maybe. Like we might know what pi naught is, but that's about it. Like even pi 1s are not known in most cases.
Sorry.
Go ahead.
Yeah, for this theorem, so the approach is similar to Woodville-Weierstrass or to prove this theorem?
To prove
yeah, this, yeah.
Yeah, it's like bootstrapping.
It's like the same, similar approach.
Yeah, this is an application, so I'm kind of just combining these big theorems. I would say it's more formal. It's just homotopy theory. Like I'm kind of translating this into pullback diagrams and stuff like that, and just applying manifold calculus to these diagrams.
You were mentioning the theorem that T1 of embedding is immersions. Do we know what T1 of Lagrangian embeddings is?
I think you do get Lagrangian immersions. So immersions end up, but you can't patch them up together.
Right.
I didn't mention this, but you can somehow formulate H principles for directed immersions also. And turns out Lagrangians do satisfy directed immersions H principle, but not directed embeddings H principle. Yeah.
Any other questions, comments?
I think we could develop it, maybe just one project, I don't know, develop a spectral sequence similar to ours to compute this.
Yeah,
that's embedding, totally real,
Exactly, it is T infinity. So, your spectral sequence should compute, it will have a different E1 or E2 page. Like it will start at emergence of that instead of emergence. Yeah, like I'm actually very interested. For example, sorry, can I take one more minute? Like why you know these two spaces are different is exactly by theorem of Gromov, which says that totally real embeddings of S3 in C3 is not empty, but Lagrangian embeddings of S3 in C3 is empty. So in fact, this is so dramatic that it's taking a completely empty space and creating something not empty. But we don't know. I don't think we know exactly what this space is. We just know it's not empty. And so it would be nice to actually compute some. Yeah.
All right, let's thank Apurva again.